Alright, I'm addressing this problem here where we have a ball that has a launch velocity of 10 meters per second up a ramp, and we want to know how long it takes from when it goes from 0 to 5 meters. Now we could have done this saying what is the change in position. So we could have said what is the change in position equals 5 meters of the displacement, and that's an equivalent statement. I did forget one thing on here, that the acceleration is going to be 4 meters per second down the ramp. Because it's slowing down, it needs to be considered as negative 4 meters per second squared. Now I will note I'm writing on my iPad here, and so that's why the writing does not necessarily look super legible. So here's our problem. And so what I'd like to do is draw a couple of graphs first to get a picture of what's going on. And so I'm going to draw a velocity versus time graph first, because I think that's a little bit more clear with what's going on here. So for our velocity versus time graph, we've got an object that is starting at a velocity of 10 meters per second. And it's going to get slower and eventually hit 0, and then it's going to speed back up, but in the negative direction. So I should have actually drawn an axis that goes down further here. That was kind of my bad. And so this is the point at where the ball hits the top of the ramp. And then this down here is the ball speeding back up in the negative direction, so that's when the ball is rolling back down again. So we've got the ball rolling up the ramp is this section, ball rolling back down the ramp is this section. Now one thing you need to know about velocity graphs, they don't show you any position data. They do show you how far you went. And so one thing we could do with this graph if we wanted to is we could say, okay, well, we know that area has something to do with displacement. So we could try to find some area. We could cut off some particular time. Let's say we cut it off right here. We could say, okay, we need to find this time such that this area is equal to 5 meters. And we could do that. I'm not going to approach the problem that way, but it would certainly be doable that way. So I'm going to take a look at a position graph now. And so now if we look at our position graph, we've got position versus time. And that graph is going to look like a parabola. And I didn't start it at 0, but I meant to. That's the iPad for you. So it starts at 0 and then goes up and comes back down again. So I'm going to quick try to do there we go. Okay. So now I'm going to go back and I'm going to redraw that, and I'll actually do it in a different color too. So our parabola is going to look something like this, where this is the top of the path, just like we have the top of the path there. And so on this graph, what we want to find, no, sorry, we don't want to find the time to the top, we want to find the time to this 5 meter mark. So you'll notice that it crosses twice. So that makes sense, because as the ball goes up, it's going to hit the 5 meter mark once, and then as it comes back down, it's going to hit the 5 meter mark. Now that's assuming the ball actually makes it 5 meters. And so what would happen is if we solved our problem and got no solution, that would mean that it doesn't actually make it 5 meters. So we're going to go to a new slide here now, and I'm going to start looking at what we're going to do to solve the problem.